Welcome back. Let's talk about Friedel-Crafts reactions. Specifically, let's start with the Friedel-Crafts alkylations. So in the previous video, we talked about how we can install a halogen, specifically a bromo or a chloro substituent onto the benzene ring via substitution reaction. And what we're going to show you now is a very similar reaction, but this time around one that allows you to install an alkyl group onto the benzene ring, so that you can start growing up that carbon chain on your aromatic ring. So the way this works out is that you do need an alkyl halide, and the alkyl halide has to be activated as an electrophile in the presence of aluminum chloride. Much like iron 3 chloride, aluminum chloride serves as a Lewis acid that withdraws electron density away from the carbon center, the R group, and that makes the R group very attractive to the benzene ring. Or to put it another way, it makes the benzene ring a lot more willing to undergo the substitution reaction. Now, ultimately, for this to work out, you do need not just an alkyl halide, but you're going to need an alkyl halide that produces good carbocations, because in essence, the reaction with the Lewis acid enhances and promotes the carbocation formation of the alkyl group. So what that also means is that your alkyl halide cannot be one based on sp2 hybridized centers, such as the benzene ring. Like you cannot use a chlorobenzene ring as the electrophile, like that will not work. But the same thing happens with vinyl halides or even alkyne halides. You don't really produce good carbocations because they don't have a good way of stabilizing themselves. So you're basically constrained to sp3 hybridized carbon chlorine, carbon bromine, carbon iodine bonds. But here's the deal. Since you're going to be dealing with carbocation formation, rearrangements of the carbocation backbone are actually possible before the substitution takes place. So you have to be very careful as to what you choose to be the alkyl chain that you're going to install on the benzene ring if you're going to go via the direct alkylation, the Friedel-Crafts alkylation route. And to make matters a little bit more difficult, you cannot really do this reaction if you already happen to have substituents on the benzene ring that have the characteristic of withdrawing electron density away from the ring. And we'll talk about what that means exactly in just a few lectures from now. All right, but let's show you an example of how this plays out. So let's say you have isobutyl chloride, and you want to install this on the benzene ring. Now, the idea right here will be that you would ideally want to get the attachment to the benzene ring through the blue bond that you see depicted right here, which is basically where the leaving group is located. That's what you would think initially. But the first step allows for the formation of a carbocation. Specifically, the chloro substituent binds to the aluminum center, the Lewis acid center. It creates this complex, which, due to the fact that the chlorine now has a positive formal charge, allows the electrons from this carbon-chlorine bond to flow towards the chlorine and create the carbocation. So in the next step, you literally undergo the carbocation formation. So these electrons move over to the chlorine exclusively, and you form your carbocation. Now, it is at this point that benzene has to come by and attack the carbocation to start the substitution reaction. But the reality is that the time that it takes a benzene molecule to diffuse close enough to the carbocation to start the reaction versus intramolecular reactions that can happen in the carbocation itself, they're not even on the same level at all, right? The carbocation is going to react with itself a lot faster than the benzene ring has time to even reach the carbocation to start the reaction. So what you should notice right here is that the carbocation we generate in the reaction is a primary carbocation. However, the carbon center next to it is a tertiary carbocation. And so a hydride migration, a rearrangement is going to occur such that you end up forming the better carbocation. In other words, the tertiary carbocation. So what you're basically saying right here is that it will be a very fruitless endeavor to try to make isobutyl benzene via a regular Friedel-Crafts alkylation because you will undergo this carbocation rearrangement. In essence, you'll end up with a T-butyl substituent as opposed to the isobutyl. And just to kind of be fair to the reaction, this doesn't always happen. You don't always have the option of undergoing rearrangements because maybe the carbocation you generated to begin with is the best carbocation you're going to get. So in those cases, rearrangements are not going to happen. But you still have to keep in mind that it is a possibility. So you got to check with your neighbors, your carbon neighbors, and see what happens. Okay, so now that we have the more stable carbocation, the benzene ring finally comes by, attacks with one of its pi bonds. In the process, you end up with this T-butyl substituent attached to it. You have the carbocation adjacent to that carbon, and in essence, you form your Meissenheimer complex yet again. Now, finally, just like you saw with the bromination and chlorination reactions, the tetrachloroaluminate derivative that we formed a few steps ago comes by to finalize the process. In essence, the chloro substituent that's drawn out here attacks with its two pair of electrons to remove the proton of the Meissenheimer complex and reinstate the aromaticity of that ring. So at the end of this process, you end up with T-butyl benzene. So, so that's kind of the idea. Now, another thing that you have to kind of keep in mind too, this is another complication that does arise from this, is that as we're going to discuss a little bit later in the lecture, alkyl groups are substituents that pump in electron density into the aromatic ring, making it a lot more nucleophilic. So the moment you stall an alkyl chain on the aromatic ring, you are basically enhancing the chance of the benzene ring to undergo further alkylation. So that is potentially something that could happen. So that's another thing you have to watch out for. So it's not only carbocation rearrangement, but also polyalkylation that may very well happen. Okay, so to kind of circumvent some of the drawbacks that I just mentioned from the Friedel-Crafts alkylation, there's also what we know as the Friedel-Crafts acylation. And the only difference right here is that instead of using an alkyl halide, we're using an acyl chloride. And just to remind you, you can easily generate acyl chlorides by treating carboxylic acids with thionyl chloride. So these are relatively easily accessible molecules. And in some cases, you can actually buy them straight out as the acyl chloride directly from a vendor. So they're relatively easy to come by. And if not, you can relatively easily make them in a laboratory. So the reaction actually happens in the same exact manner. You still treat it with aluminum chloride as a catalyst. You undergo the substitution, like we discussed in the previous reaction. But here's the deal. When you do an acyl chloride reaction, there is no rearrangements on the carbon chain. And that has entirely to do with the presence of that oxygen. You'll see momentarily why that's the case. But the other thing about it too is that when you have this carbonyl functionality, basically, a ketone functionality, perhaps aldehyde functionality, but when you have a carbonyl functionality like this, there's a very simple way to get rid of the oxo group. Pretty much, you can treat the aromatic carbonyl substituent with elemental zinc in aqueous HCl solution. And with a little bit of heat, ultimately what we end up doing is removing the oxo group as water and oxidizing zinc to zinc 2 plus, right? So the idea is that you could install an acyl group onto the benzene ring and then turn it into an alkyl group after the fact. And because the acylation step does not carry rearrangements, this is an alternative to the problem that I mentioned with the alkylation reactions. So this is really a powerful method to kind of, have handy for your synthetic tools. Now, all that being said, this is not going to work out if you already have substituents present on the ring that are strongly deactivating groups. But they have to be strongly, so mid to strongly deactivating groups will prevent this reaction from happening. So that's the only thing to watch out for. But aside from that, it's a really great alternative. So as far as the reaction goes, the mechanism that is, the chloro attacks the Lewis acid center, just like we saw in the alkylation reactions. The formation of that positive formal charge on the chloro group allows for the electrons of the carbon-chlorine bond to completely depart and just belong to the chlorine exclusively, leaving this carbon with a positive charge, a carbocation. Now, because of the presence of oxygen, the lone pairs of the oxygen can easily move over as a resonance structure to create a stabilized derivative that is got a full octet for all the second row elements present. And in this case, now the oxo group has a positive charge. We call this the acylium ion. And it is because of this formation, this stabilization via resonance, that any rearrangements of the carbon-carbon chain is completely prevented. So now, for the sake of the mechanism, you could always keep it just as the carbocation version of it. It's technically the same thing. But the benzene ring attacks the carbonyl carbon, which is technically carbocation at this point. You create the Meissenheimer complex, just like we saw before. And the end point is that the tetrachloroaluminate byproduct comes by, attacks the proton, the electrons of the CH bond move over to reestablish the aromaticity, and then you create your acylated product. And what you should notice right now is that, technically speaking, this was a primary center, and next to it we have a tertiary center, but a rearrangement has not happened. So we still have attachment directly on the carbon where the leaving group used to be. And last but not least, if you actually wanted the isobutyl substituent as opposed to the ketone substituent, you could treat this with zinc in the presence of acid. First of all, the ketone will be protonated to give you this derivative. Zinc will at that point interact with the carbonyl. Basically, it will oxidize, donating its 2 electrons to that carbon center, kicking away the electrons from the oxygen and forming this zinc alkyl derivative. Now, since this is all done in the presence of acid, the carbocation that has been generated is going to be ultimately reprotonated by HCl. You'll kick out zinc chloride in the process, but now you have an alcohol out of this thing, and then the process continues because the alcohol can be protonated by HCl, and the water leaving group that you have now is perfectly situated to be kicked out by another equivalent of zinc that, upon oxidizing, ultimately kicks out the water leaving group, produces another zinc carbon ion, and then the presence of the acid allows you to ultimately protonate that to give you the alkane. Now, one last thing I mentioned right here is that because of the fact that you are next to a benzene ring and you have the option for resonance structures, this reaction could very well undergo an SN1 reaction type of event before zinc attacks. But aside from that, the mechanism yields the same product altogether. So this is a really great way to circumvent the drawbacks of what happens with alkylation reactions. So just make sure to keep in your arsenal of synthetic attacks. All right, and with that said, we'll stop the video right here, and in the next one we'll talk about sulfonation and nitration. So see you in the next one. All right.